All right, so welcome back. Today we're going to talk about reductions and formalize the concept, and then we'll do some reductions on Friday and going into next week, as many as we can. There are different notions of what are called reductions, but before we do that, let's make sure, let's make sure that the audio is working, but also let's take stock of where we've been so far. So complexity theorists like to draw the complexity landscape using Venn diagrams, but not Venn diagrams as in like, you know, a bunch of circles or anything like that. Instead, these arcs, okay? So I'm not even sure. Yeah, there we go. That looks nice. So what I'm going to do is I'm going to say that this is the class, this is NP right here, right? Remember that NP is non-deterministic polynomial time. It is not non-polynomial time. We don't know whether or not this is equal to P or not, but we do know that P is contained inside of this. There we go. And so I'll put this as P, okay? So the reason that we like to draw the complexity landscape like this is because it gives an intuitive notion of relative complexity. That as you go up, it is more difficult problems, or more complex. Now, it's not as simple as strictly more, because again, we don't know what this landscape looks like. It could be that P is equal to NP, and if that happens, then what happens to this entire thing up here? It collapses down to P, all right? We don't know that. We also don't know whether or not, you know, what about this area right here? Are there problems in NP that are not in P? If we could establish that, then that would actually show that P is not equal to NP. And we don't know either one of these things. Right? But to even begin to answer that question, what we need is a way to, we need a framework for saying that this problem is at least as hard as this problem, or that problem is no more difficult than another problem. So let's go ahead and draw what we do know here, for example. Give me one problem that's in P, that has a Turing machine or has an algorithm that is a deterministic algorithm that solves the problem. Yeah?
Binary sort.
All right, so searching.
Yeah,
Sorting. Now remember that linear search and binary search are two algorithms that solve the same problem under different assumptions. So you can select, just like selection sort and quick sort, they're two different algorithms. One is clearly better than the other in terms of efficiency, but they're two algorithms. This is a landscape of languages or problems. There are no algorithms here at all. The existence of an algorithm puts a problem in a particular complexity class. The existence of selection sort, for example, puts the problem of sorting down here in P. Right? Any of the graph problems that we've looked at so far, right? Except for one particular one, Hamiltonian path. Right? That's up here somewhere. We don't know any polynomial time algorithm for this. What about SAT? Right? Satisfiability. We know a brute force version of that, where you can go ahead and try every single possibility, just like we have a brute force, and you programmed a brute force for Hamiltonian path on your first assignment. And those are both in NP. But are they in P? That's the big open question. So even though I've drawn it like this, where there are more difficult problems up here, and down here there are less complex problems, right? It's just a way of thinking about it. What we need to do is we need to establish some framework that says that given this problem, given problem A, we can establish a relationship between them. This is called a reduction. Now, what this does visually here is it establishes that A is no more or that B is no. How do I want to say it? Let me go ahead and write it out, and then we can look at this symbol. And this is a very cognitive choice on the behalf of complexity theorists. This establishes a relative complexity of this. B is at least as complex as A. Right? Or another way of saying this is that A is no more complex than B, right? That's why we're using the less than or equal to sign here. It could be that they have the exact same complexity, right? That A is equal in terms of complexity here to B. If you looked at searching and sorting, and you'd see that they're in the same complexity class right here, P, then you would say that they have an equal, yes, one of them is order n squared algorithms, one of them is order n log n, or order n log n algorithm, whatever. It doesn't matter. They have the same relative complexity speaking with respect to polynomial time. Right? Now, what about establishing other problems? Like, what about these two problems? What's their relative complexity? What about this class of problems and this class of problems? What's their relative complexity? We have to come up with a way of saying that this problem is no more difficult than that problem over there. Yeah?
So the P next to the D, is that like sort of like a...
This is polynomial time. We'll get to that here in a second. But this is a reduction under polynomial time reductions. There are dozens and dozens of types of reductions. In fact, what I'm about to show you here is called a Turing reduction, which is a different kind of reduction. You have truth table reductions, you have mapping reductions, you have a whole bunch of, dozens and dozens of just different ways of looking at relative complexities. We're going to keep it simple, and eventually we're going to look at polynomial time reductions as I've written here. But to understand this a little bit better, I wanted to look at an actual example. A lot of people, when reductions and complexity are first introduced, whoa, this is lost. I'm completely lost here because this is all math. This is all theoretical computer science. It's not. You've been using reductions since you began programming. Right? When one function calls another function, that is a reduction. That's all it is. Right? So let's take a look at this example right here. Let me go ahead and increase the size here. Right, there we go. This is Python code. It's not real Python code because, but you've done stuff like this before already with your previous homeworks. And so I've defined these four functions here. Right? Each one of these functions is a generic algorithm that solves a problem. For example, is path. What problem does that solve? It determines if there is a path in G between X and Y. Directed, undirected, it doesn't matter. Right? This is the connectivity problem. Right? So this algorithm right here, this function, solves that problem. What does the code look like? I don't know. That's to be decided another day. What about this one? Get path. It returns a sequence of list of vertices connecting X to Y if one exists. It returns none if no such path exists. Okay? So that's a slightly different problem. Rather than just answering the question of whether or not a path exists, it's the functional version. This up here is the decision version. This right here is the functional version. I don't want to know just does a path exist. I want to know what that path is. Right? In other words, I want more information. That sounds provably more complex to me, right? Or at least as complex. Right? Might be a little bit more complex. I don't know. What about shortest path length? Now that one, you could run Dijkstra's algorithm, right? And then that gives you the shortest path from A to B. And then you could say, all right, well, it's of weight 5, return 5. Versus actually computing the shortest path, which is going to be a list of vertices. So what about the relative difficulty of each one of these things? Right? How would you go about programming these things? Would you run let's take these first two here. Would you run DFS, BFS, cut, paste, adapt, cut, paste, adapt? That's not how you program, right? Programmers like to be lazy. They like to reuse code. Theoretical computer scientists are even lazier. They like to reuse theorems, right? So, how would you go about implementing, say, is path or has path? If you want to call it has path instead. Is path. I just wanted to determine yes or no, there is a path. Right? Yeah, go ahead.
Does G have are we assuming that G has a list of, like, different edges?
I don't care. It's network X, right? Let's say. G is a network X graph. Right? suppose somebody did this for you, right? So you're teaming up with a partner, and they draw the short straw, and they end up having to implement this one. So suppose that this is done, right? Assume this is done, right? It's not real code. How do I implement isPath? Yeah. Get path. All right, so P is equal to get path. All right, X, G, X, and Y. Now, I've gotten a path from this other problem over here. How can I use the solution to that problem to solve this problem over here? All right, return false. Oops. It is actually Python here now. All right. All right, good. Code reuse, right? That's a reduction. This is technically a Turing reduction because what you're doing is you're assuming that there is this algorithm for getting a path. Algorithms are Turing machines. So you're assuming that there's this Turing machine over here that you can run on the input, and that Turing machine accepts or rejects. And whatever, if it accepts or rejects, then you can take that output and you can use that output to solve this other problem over here. Okay. Well, now we drew the short straw. Get path. Could I use isPath? G, X, Y in some way? Well, now A calls B, B calls A. Right? We're just going to have an infinite recursion back and forth. Right? Nope. All right. How could I use one of these other functions and again pass the buck? Right? Pass it on to the other partner. All right. Do shortest path length. Say the length, right? Of G, X, and Y. Right? K is equal to. Right? Now, how can we use that to determine if there is a path or not?
Could the path length still be 0, like if some like edges are negatively weighted?
We don't worry about the small details like that.
Oh, okay. So yeah, if k isn't 0, then.
All right. So, okay. So if k is less than infinity, right? Otherwise, we'll say over here that the shortest path length. We didn't put that in the documentation, but let's go ahead and do that. We'll go ahead and say vertices x and y in the graph G returns, what is it, math.inf? What is it? Inf if no such path exists. Okay. All right. And so if it's less than, is that how you do inf? Okay. Or all right, it's highlighting it, so I'm sure that it is. Okay. Then return. Actually, can we use the length here? It's 5, right? Does that tell me what the actual path is? No. So what could I do instead?
The actual shortest path.
Okay, return the shortest path, right? X and Y. And if there is none, then we can put that in the documentation down here that it returns an empty list or none or something like that. Return. Right. Great. All right. Now, what about this? Shortest path length. How could I implement that without writing any substantial code?
You can do like call the shortest path function.
All right, shortest path of G, X, and Y. There we go. Oops, that's not what I want. And then do what? Length of the path. All right. Now +1, technically. Why? It depends on the implementation details, but if you go from A to B to C to D, and it only returns these two, then you would need 1, 2, 3 edges. It all depends on how you're actually going to implement this. At the end of the day here, this is the real algorithm, right? And like any good computer scientist, I will go ahead and put in a to-do, because I still don't want to do it. All right, that establishes that each one of these problems is no more difficult than the one down here. There's your reductions. So let's go back over here And using the same kind of landscape here of more difficult and less difficult, let's write out these these four problems with respect to the overall difficulty. Well, this is the one that I didn't know how to do, or I would pull in, Dijkstra's algorithm or something. So that is clearly I don't want to say strictly greater than, because it could be less than or equal to, but that is clearly the most difficult problem, right? So I'm going to write that at the top, right? Shortest path. And this is the functional version. Why is it the functional version? Because it actually returns the path. It gives you the solution. Where would I write the rest of these? IsPath uses getPath, and getPath uses shortest path. So this is all transitive here. What was it called? Compute path. Let's say compute path, which is also a functional version. And then finally, down here, the least most difficult thing among these four problems is going to be IsPath, or IsConnected. And this is the decision version. Remember, because we're only returning true or false, we're accepting or rejecting if we were talking about it in terms of Turing machines. What about that other one, shortest path length? Did we establish any sort of relationship between these two? Nope. But we did establish a relationship between shortest path and shortest path length. Right? So these are reductions. If you can use a solution from one problem to solve another problem, that means that this problem over here is no more difficult than that problem over there. So let's look at this from a more general abstract landscape now, right? So if I go with A reduces to B, then this establishes several things. First of all, solutions to B can be used or adapted to solve A. Right? And note here that we use them directly, either returning the exact same solution, or we adapted it by saying, if it's none, then output false. We took a functional version and converted it over to a decision version, right? Or actually the other way around. We took a decision version, converted it, or reduced it to a functional version. But otherwise, here we were just using the exact same solution. Here we had to adapt it a little bit. Here we had to adapt it even more, right? Not only did we have the functional version, but we took that and we asked, well, what's the length of that path? And that's my solution for this one, right? So it establishes a relative complexity. B is at least as complex or difficult as A. From the perspective of A is no more difficult or complex than B. And so we have a symbol to write that down. We say that A is less than or equal to B in complexity with respect to polynomial time reductions that we'll define here formally in a moment. But this is the intuition. Right? This is the intuition that you should take away from this. Here's another picture of it. Okay. Let's see, where is it? Okay, maybe it's not in here. Oh no. Oh, there it is. Here's the reduction, or here's an idea of a reduction. Okay. So we've got A here, and A is reducing to B. We take an input X for A, right? We're trying to run this function on this input right here. We're trying to run this algorithm on this input right here. We're trying to run this Turing machine on this string right here. Right? All three of those statements are exactly the same thing if you accept the Church-Turing thesis. Okay? Once we've got this input, we go through what's called a mapping reduction. Right? In other words, we take an instance of X, which is an instance of this problem A, and we transform it into an instance Y, which is an input to, or an instance of this problem B over here. Okay? We use this purported solution for B, right? And depending on the outcome of that, we answer yes or no, or we flip it, or we condense it, or like we did over here, we took the length of the returned value, the output value, right? We are transforming it somehow, taking this output and then creating our own output over here. Right? You do this all the time. Function calls function, calls function, calls function. Right? This is simply a function, an algorithm, a Turing machine, that invokes another function, another algorithm, another Turing machine as a subroutine. That establishes that this problem is no more difficult than this problem. Because if you have a solution to this problem, guess what? You have a solution to this problem. Right? All you have to do is use this as a subroutine. Yeah?
I guess in the example we did before, the functions we use to solve like the ones more towards the bottom seemed like easier than the one like immediately after it, right? Or like sort of like less complex. But I guess my point is like, is there a difference between like sort of using a function that gives like sort of like less detail to solve a function that has more detail versus like just
you're talking about going the opposite direction here.
Yeah.
A reduction, again, the notion of the word reduction doesn't really make sense. I agree. In plain old English, what is a reduction? You're making something simpler, right? That's my intuition when I hear, if you just take a non-computer scientist person and ask them what's a reduction, is it taking something that's complex and making it simple? Yeah. Or is it taking something simple and making it more complex? No, that doesn't sound right, right? And so I agree. That does not sound right. Right? You're talking about a reduction should be going down, right? A reduction in cooking. You're evaporating water to make a sauce more concentrated, right? You're reducing it, right? You're taking things out. You're making it simpler, right? You're focusing things. And unfortunately, that's not what this reduction means. A reduction simply means that you're establishing a relative complexity, and unfortunately, the intuition goes the other direction for computer science, right? Just like our trees grow in the wrong direction.
Is it because you're reducing it to a problem you hope has already been solved?
Exactly. All right. So from that perspective, you're making it simpler, right? You're coding simpler here in that I only have to make. I like that. That's the first time I've ever actually thought of it that way, where you're reducing the complexity because you already have this off-the-shelf solution over here called, I don't know, Dijkstra's. Right? So you are reducing the amount of work that you have to do to solve these three problems up here by transforming it and passing the buck to another person, passing the buck to Dijkstra over here to get them to do it instead. Right? I like that idea. Right? All right, so more formally here. Let me go ahead and cut and paste this stuff here. All right. Oops, that's not it. That's not what I want. Here we go. All right, so there we go. Our goal is to establish a relative complexity of problems, not algorithms. Algorithms, their relative complexity, two algorithms that solve this. We want to deal with language problems, which are languages, not algorithms. In general, you can use or adopt a supposed solution for B to solve A. Then we say that A is no more complex than B. Right? Or from the perspective of B, B is just as complex or even more complex or hard to solve than A. Right? We're not making A simpler. We are reducing A to B. Right? Again, I like this new interpretation on a possible new interpretation. We are reducing the amount of work we need to solve A by using an existing solution for B. Right? By reducing it to B, we've reduced our own amount of work. Right? Another way of saying this is that I don't know how to solve A. Right? I don't know how to solve is path, right? Because I've never seen BFS or DFS. But I have seen Dijkstra's. Right? I do know how to solve B, which is the shortest path. Right? So I could use the solution for B, the more complex problem, and use that as a solution for this problem over here. Right? And that reduces my work, right? I've reduced the problem of solving A to the problem of solving B, and that's it. Right? And then we use this symbol right here, less than or equal to, with a little p down below to indicate that it's a polynomial time reduction. Now, what is that exactly? Right? So polynomial time reductions are everything that I just showed you over here, by the way, is technically a Turing reduction, because you're not, I'm not worried about the resources required to actually compute this function. It could be polynomial time, it could be exponential time, it could be super exponential time. Right? It could take 2 to the 10 to the n factorial to the n factorial to the n factorial time. I don't care, right? It's just a Turing machine exists, an algorithm exists that can solve this problem. But now I am concerned with resources, because I am in the world of P and NP. X, remember X from yesterday? There's also this a world of exponential time algorithms, or exponential or problems that can be solved in exponential time, right? I'm not even looking at that high, right? There's an infinite hierarchy going all the way up here. Right? All I'm doing is considering P and NP. So if I'm focusing my world down onto these two complexity classes, I also need to focus my resources down onto these two complexity classes. We only want to use the power of P to do our reductions. So we can only use the power of polynomial time, deterministic, to perform our reductions. Right? Why? If we used anything more powerful, we'd be cheating. Right? What if I use the power of NP? Remember, NP can solve satisfiability, right? If I just use the power of NP to solve satisfiability, then of course that's trivially reduced to itself. What I want to do is I want to establish relative complexities among problems in the same classes here. This, or between those two is actually what we're going to do. Right? And if I'm allowed to use the power of the entire class, everything is equal. Right? Because if something's already in here, well, I can solve it with NP. So there is no sense in reducing one way or the other, right? You're reducing A to A, you're reducing B to B, you're reducing 1 to 1, 2 to 2, right? They all have the same complexity. So what I want to do is to establish relative complexities between these two complexity classes, I have to restrict my power to the lesser one. Right? And that's why we call them polynomial time mapping reductions. Right? So here's my definition. Here's the formal definition. I'll cut and paste this so I don't have to write the LaTeX. Let P1 and P2 be problems. Note the different font here. We're not talking about the complexity class P. That's done in usually a serif font or a sans serif font, whatever it is. We say that P1 reduces the P2, and we write that P1 is less than or equal to, and then here's where the sans serif font comes in. Right? That's the complexity class P to P2. If there exists a function f such that f maps all yes instances of P1 to yes instances of P2, or no instances likewise, and f has to be computable by a deterministic polynomial time Turing machine. Now, that's the technical definition. Let's go back to that picture and understand it a little bit better now. Again, I am taking instances of one problem, and I'm shoving it through this mapping reduction, this f right here. F is restricted to the power of p. Right? It can do anything that you can do in polynomial time. You can do searching, you can do sorting. You can take one graph and transform it into another graph. Right? You can take the input and simply just map it to the input like we did over here. Did I change the input at all? Nope. I just handed it off to another function. So that's clearly computable in polynomial time. Right? But once you have this new instance of another problem, then you shove it through this purported solution for the other problem. And if it's a yes instance, a decision version, for example, then you output yes. If it's a no instance, then you output no. Right? Now, technically, it doesn't need to be yes to yes, no to no. You could, of course, flip them, right, if you needed to. But it preserves all solutions. That if there you're not gonna, it's not gonna break down, basically. That if you, another way to put this is, it's calling this subroutine is not going to screw up the entire process, right? It's going to preserve solutions, right? That's what I should say. Is preserve solutions. Okay. So now this allows us to define, again. Let me go ahead and back this up. Sorry. There we go. A problem in the complexity class NP is decidable by a non-deterministic Turing machine. We defined that last time. But now that I have reductions, what I can do is I can start establishing what are called complete problems. A problem is NP complete if every problem in NP reduces to it. Okay? That's basically establishing that this NP complete problem is the hardest of the hard. Right? So let's come back over here to our complexity landscape and redraw it. There we go. Here's NP. Here's P. And now we have this new class of problems called NP complete. What I'm going to do is I'm going to establish that up here. Right? Now remember, we don't know if P is equal to NP or if it's not equal to NP. If they're equal, of course, this entire thing would collapse down to just P here. Right? And this and everything in here would all be equal to P, if P were equal to NP. But what this does is it oops, that's not what I wanted. This establishes a new class of problems called NP complete problems. This is NP complete. These are the hardest of the hard. By definition, everything in NP reduces to it. Anything in this complexity class P reduces to it. Anything in this intermediate class, if there is such a thing, and we do know that if P is not equal to NP, then there are problems in this is called NPI, NP intermediate. Anyway, every problem reduces to this NP complete problem, including what else? By definition, all other NP complete problems. Right? Everything reduces to it. It is the most difficult or most complex of the complex. And when I say the complex, I am of course restricting my attention to this landscape right here, NP. There are complexity classes that go above this all infinitely. You can define this infinite hierarchy of stuff. Okay? All right. So yeah, go ahead.
So something is like polynomial time reductions if the inputs that you have for like the is path, for example, if it takes you a polynomial amount of time to translate your inputs for is path into get path,
yes.
Then
this thing right here, that's the transformation.
okay.
That has to be deterministic polynomial time.
Does it necessarily matter whether get path is polynomial time or not?
Well, if this is not polynomial, then we don't even have to know whether or not an algorithm exists for this, for the reduction. Right? So if this ends up being NP, well, that's still okay. You can always reduce a simpler problem to a more complex problem, right? And then you still have the power of NP, and then you can solve that problem. That doesn't establish any relative complexity, though, right?
Okay.
What's going to establish a relative complexity is that first NP complete problem, right? Why is it good to talk about this NP complete problem? Because all I have to do is come up with one algorithm, right? If we found one algorithm that solved an NP complete problem, and it ran in polynomial time, then what would we have established? Remember the complexity landscape here, right? I've got one NP complete problem. I can take any problem here and reduce it to this one NP complete problem. And if I have a polynomial time algorithm for it, guess what? That moves this guy right here down into this complexity class right here, which means that this entire thing collapses. And we've established that P is equal to NP. Right? So if I only have to come up with one algorithm to rule them all, basically, and this ends up being NP is equal to it is sans serif is equal to NP complete. Now, it is unlikely that that is the case. Most people don't believe that that's the case. So how do we go about separating them? That's an even bigger question that involves structural complexity. You would have to come up with some sort of a lower bound. Not only that, but you'd have to overcome all these hurdles that theoretical computer scientists have come up with, like, oh, well, any proof that purports to show that there's a separation has to overcome this relativization kind of idea, has to overcome this other theoretical idea that it has to jump all of these hurdles in order to actually establish this, and we just keep finding more hurdles. Right? So nobody knows how to do it one way or the other. But one easy way of doing it, probably the wrong way of doing it, is simply come up with one algorithm to solve, say, satisfiability, runs in polynomial time, and you've collapsed the entire hierarchy down into nothing. Right? That's why it's probably not that likely. Yeah?
So by saying that there, again, supposing that P is equal to NP, there would be one problem that solves all polynomial things. Let's say there's one algorithm that solves satisfiability and if the graph is connected and if
Exactly.
all these random things.
These hundreds and hundreds and hundreds of different problems that don't appear to have any connection to each other whatsoever. Some of them work on graphs. Some of them work on integers. Some of them work on sets, right? They would all be solved by this one problem. Or with not problems don't solve problems, but this one algorithm, I should say, right? If you came up with that one algorithm to rule them all, right, that's a pretty damn magical algorithm, right? Probably doesn't exist. Right? That's why it's probably doesn't exist. It sounds way too fantastical to exist. Right? Yeah.
So like a problem essentially consists if every problem in NP reduces to it. How do you know if every problem in NP?
Good question. We have to establish that. So in 1972, Cook and Levin, independently, established the first NP complete problem. We're not going to show that proof. It's not that difficult. But what they did was they took the computation of a non-deterministic Turing machine and they encoded it into a logical propositional formula. And that propositional formula is either satisfiable if the Turing machine accepts, or it's not satisfiable if the Turing machine rejects. Right? So they basically just showed the mother of all theorems showing that you can compile programs. That's all they showed. You can compile an algorithm into a logical formula that then you can go back and write a bunch of circuitry for, right? And then all you have to do is try it on all possible inputs and see if the circuit ever outputs, high voltage or low voltage. So that's what they did in 1971 or 72 or whatever it was, early 70s. And for us to establish NP-complete problems, all we have to do is take this one problem and reduce it to the problem that we're under consideration. So given a problem, to establish that it is NP-complete, I don't have that, so there we go. NP-complete. You only need to show a reduction, and I'm going to emphasize this, from a known NP-complete problem to it, right? Why is that? Because reductions are transitive. If I can reduce problem A to problem B, and I can reduce problem B to problem C, remember, it's just a mapping. Map A to B, map B to C, therefore you've mapped A to C, right? Like I did over here. Right? One function calls another function, I guess I didn't do that here, but one function calls another function, calls another function. You can compose functions, and it establishes transitivity, right? So all I need to do is establish that first NP-complete problem which Cook and Levin did for us back in the 70s. Right? And all we need to do is take that one NP-complete problem and reduce it to another NP-complete problem. Right? Why does that work? Well, let's focus in on this landscape over here. Again, if I start out with SAT and reduce it, say, to, I'll just pick something randomly here, Hamiltonian path. Right? We know that this is NP-complete, that it's in that set that I just drew as a Venn diagram up here. And that establishes that Hamiltonian path is in NP-complete. Now, why? What's the definition of NP-complete again? Everything reduces to it. Everything reduces to SAT, including things that are supposedly up here. It just reduces back down, right? So we shouldn't have written it up here. We should have actually written it down here, and it reduces to SAT. So if everything reduces to SAT, and SAT reduces to Hamiltonian path, guess what? Through transitivity, everything reduces to Hamiltonian path. That establishes that it is NP-complete as well. Let's take another example, though. What if I were to show that, say, I don't know, sorting reduces to SAT? Is that all that surprising? No, you're reducing something that we know to be efficiently solvable to something that we don't know the complexity of. So that doesn't establish anything. In fact, we already know this. Because SAT is NP-complete, by definition, sorting reduces to it. Now, you have to be careful here because, of course, this is a functional version. Given an array of elements, it outputs another array. It doesn't say yes or no. Up here, this is a decision version. It says yes, it's satisfiable. No, it's not satisfiable. So there is a little bit of incongruity here, but that's just a technical detail that you'd have to overcome. Right? Yeah?
I'm trying to remember how this works. Would this still be a polynomial time reduction?
Yes, well, yeah, it'd have to be, yeah. You can restrict yourself even further and talk about log space reductions, truth table reductions, it's AC0 reductions. Again, there are thousands of kinds of reductions. The only reduction that we're going to pay attention to is polynomial time reductions.
So, like, that means that there's like a polynomial way of translating like the inputs of the sorting algorithm into, or that translations of SAT problems into the translation.
Nope, that would go the other way. You're translating instances of SAT down to sorting. If you did that, you just showed that P and NP are the same.
Okay, so you're trying to solve sorting, you do that,
You can always reduce by Cook-Levin, and by definition, sorting reduces to SAT. I don't know how, and it's not all that interesting anyway.
And I'm just trying to get that means that you're trying to solve SAT, or you're trying to solve sorting by using SAT.
Yes.
Okay.
Yeah, I mean, the way that the way, if you really wanted to show something like that, I say that you'd probably establish this big giant propositional formula that was true if everything was in order. If A is less than or equal to B, B is less than or equal to C, C is less than or equal to D, dot, dot, dot for each element. And then you would encode that in some sort of propositional formula. And then that's true if and only if they're in order, right? So, but that, again, it's kind of useless because you already know how to do sorting. Run selection sort, and then what's your output to SAT? It's yes, and that's it. Right? It's a trivial output at that point because you've already solved it down here in P.
I was just wondering, how do you solve, in the homework, don't we have to establish the problem is NP complete or show it?
Yep, and so what we'll end out on today is a 5-step process, and this is what we'll do next time. We'll show as many problems as we can. We'll show at least 2 or 3 reductions here. But there's this 5-step process. I believe that credit goes to, for this there's a compendium of NP-complete problems. There's this book that has, maybe a couple hundred NP-complete problems in there. And it shows proofs for some of them. It used to be that you could, get published for showing an NP-complete problem. That's no longer the case. We have hundreds of them now, so that's no big deal. But in any case, they established that if you show these 5 steps, that's enough for a proof to show that something is NP-complete. First of all, you want to show that it's in NP to begin with, because if it's not in NP, if it lies outside this entire complexity domain, right? If it's way up here or something like that, it's not even under consideration, right? If it's a problem that requires exponential time, and there are problems that do require exponential time, then of course it's not known to be an NP to begin with. What we have to do is we have to establish that it's an NP. How do we do that? How did I establish that SAT was in NP? I just came up with a non-deterministic Turing machine or algorithm to do it. You have a guessing phase, you have a verification phase. That's it. That's all it takes to show that something is in NP, right? Not NP complete, but NP. You need to show these other 4 steps to go along with that. Then you take a known NP complete problem that is easily reducible from that problem to the problem that you're trying to establish is NP complete. You come up with a mapping reduction that does that, right? And you prove that your reduction is correct. That is, that it preserves solutions. That it's a yes instance down here, if and only if it's a yes instance up here. You show that your reduction is computable in deterministic polynomial time, and you're done. So for, question?
Sorry, silly question. Reduces, so part 2, select a problem that reduces from P would say that P is less than Q?
From 2. I've got both words in there, right?
Oh yeah, I didn't even realize that, but from...
Sorry.
Sorry, I'm just getting confused by the wording.
Yes, that's because I have both words in there. Okay. So you take a known NP complete problem and you reduce it to your problem P.
Okay, yeah.
I imagine that I had that in there because the last lecture I did this on, I probably said to or from, which one is it? And then we go back to this picture over here, and how did we do it over here? We took a known NP complete problem and we reduced it from that problem to our current problem. Right? So let me put both of those words back in there, and so we are going from the known NP, let me copy this, NP complete problem, going to your problem. There we go. Now I've got both of those in there.
Okay.
Go ahead.
So you called the problem P. Is that because
Yeah, that's a different font for P. Don't consider don't.
it's not
That's why we usually use L. languages, basically. But that is your problem, P. In this case, say it's a Hamiltonian path or something like that. Now, let me show you really quick here an example of what I mean. So I think it was in your homework maybe. Do you remember the click problem? Yeah, or clique.
I don't know.
Did I put that in your homework or not?
You did,
Oh.
but I don't know what.
I did, or did not?
You
Alright.
put in one or two problems
So,
involving
a clique
I don't know what that is.
is a subset of vertices that are all connected. So, for example, what's a clique here? 1, 2, 3, 4. They're all connected. So there's a clique of size. Oh, here, I'll use K instead. Here, there's a clique of size 4. Okay.
And all three or all four are connected.
All 4 of those are connected to every single other vertex in there. Now, why can't I include this one in my clique? Because it's not connected to any of them, right? Okay. That's an NP-complete problem. Let's take the same, we're over time here, but I can go ahead and finish up really quick here. Come on, copy, copy, paste. Okay. Now, what about a similar problem is independent set. Right? An independent set is a subset of vertices that such that none are connected. Right? So what's a independent set over here? If I take this one, and I take this one, and then that kills that, so
Oh, wait, yeah.
let's take this one and this one. Right? Those 4 green ones are not connected at all, right?
So
Oh, darn it. Yep, you're right. So yes, that killed that one. So there's an independent set of size 3. Finding a maximum clique and finding a maximum independent set are both NP-complete problems. What's a reduction between the two? So between now and Friday, think about that, and the hint that I'll give you is think about the complement graph. What happens in a complement graph? Same vertex set, and if there's an edge in the first graph, that edge is gone over here. If there's no edge over here, that edge is drawn over here. Right? So how does that change an independent set into a clique? How does that change a clique into an independent set? Think about that. It might be on your homework, so really think about that. All right, on Friday.